Good morning, and thanks for joining my talk. I'm Alejandro Perez, and today I will discuss the classical and stochastic delta and formalisms as tools to study the non-Gaussian PDF of scalar perturbations from inflation. I will start by introducing the classical and stochastic delta and approaches and show how we can use them to compute the fully non-Gaussian PDF of curvature perturbations. I will then discuss the validity of several standard approximations in the literature before going to the main point of my talk, which is the comparison between these two formalisms. And finally, I will discuss some subtleties and caveats regarding this comparison. The backbone of the delta formalism is the so-called delta formula, which is a fully nonlinear formula between the curvature perturbation coarse-grained on superhorizon scales and the inflaton and momentum perturbations. In this case, derivative is with respect to the number of evils. The way to interpret this nonlinear formula is the following. We pick an initial time, a reference time, which we call Ni, which has to be subject to the condition that all the linearized Fourier modes of interest for the physical process we want to study have already frozen at the time Ni. So at this time, we have some background field and background momentum value, which we perturb with delta phi and delta pi, and we compute the number of evils it takes to reach from this perturbed field momentum configuration to some later stage in inflation, let's say the end of inflation. And from here, we subtract the fiducial number of evils that it takes to reach the same later stage, configuration from the unperturbed initial configuration. And this difference in the number of evils, which is what we define as delta n, coincides with the frozen nonlinear curvature perturbation defined on uniform density slices. The important point of this formalism is that provided that we did the right choice of Ni regarding the frozen modes, we can use the separate universe approach, which means that this number of evils can be computed by solving the unperturbed Friedman equations. Once we have computed this nonlinear relation between curvature perturbation and inflaton perturbations using the delta n formula, here is where the two formalisms arise to compute the PDF of zeta. In the classical delta formalism, we simply perform a change of variables in the PDF of zeta. So even if delta phi is Gaussian, as we will assume, the PDF of zeta will be non-Gaussian because of nonlinearity. The stochastic delta formalism is a bit more convoluted because in this case we use the stochastic formalism of inflation to solve the dynamics of the field with the usual equations supplemented with these stochastic noise terms that account for the backreaction of short wavelength modes when they become superhorizon and kick the background, with a variance that is proportional to the power spectrum of inflaton and momentum perturbations. An important parameter in this stochastic inflation approach is this sigma, which we call the coarse-graining parameter, which informs us of the delay between a mode crossing the horizon and the same mode kicking the background. And the way to compute delta n in this case is by simply solving the stochastic equation several times with these stochastic sources and comparing the number of evils it takes to end inflation with the fiducial number of evils when the noise is set to 0. An important consistency condition that actually follows from the separate universe approach we mentioned in the last slide is that momentum perturbations have to be proportional to field perturbations with this kind of proportionality factor, and a similar consistency condition holds for the momentum noise and the inflaton noise in the stochastic approach. The delta formalism tells us nothing about the statistics of field and momentum perturbation. This has to be set as an external input from some other theory. In classical delta formalism, the most usual choice and the one we'll use to produce the plots I will show you in the presentation is to take delta phi and delta pi to be Gaussian in consistency with linear perturbation theory with a variance which is the integral of the power spectrum. In the stochastic delta formalism, a similar assumption about the Gaussianity of the field is applied, which in this case is encoded in the statistics of the white noise that sources the stochastic differential equations for the field and the momentum. Right, so let us now focus in the more particular case of inflation we want to study. We want to study single field inflation models which feature a phase of ultra-slow roll achieved by the usual local minimum, local maximum configuration in the potential of the inflaton. This leads to a slowing down of the inflaton, which enhances scalar perturbation and produces a peak in the power spectrum. And this ultra-slow roll phase is typically followed by what we call a constant roll phase, which is a phase in which the second slow roll parameter is constant but not necessarily small. The delta formalism is most easily understood by looking at the phase space of ultra-slow roll inflation. So let me take a minute to introduce the different elements that appear in this kind of phase spaces. The origin of these phase spaces is located at the local maximum of the potential. The inflaton rolls from right to left, so the local minimum of the potential is somewhere here, outside of the plot. The gray lines correspond to trajectories of the inflaton that end inflation, meaning that they go towards the absolute minimum of the potential, while the red trajectories correspond to trajectories of the inflaton that get stuck in the local minimum, which is outside of the plot. The black dashed line is the background or unperturbed trajectory of the inflaton. So going upwards here is the ultra-slow roll phase, in which the inflaton decreases. You can see that the velocity becomes smaller and smaller, and then it accelerates back during this constant roll phase. And indeed, this is a constant roll phase because from the equations of motion, it can be seen that the tangent to these trajectories in phase space is precisely eta. So a constant roll phase in phase space simply consists on a straight line. So this part here of the background trajectory, which is straight, this is the constant roll phase of the background trajectory. How does the delta M formalism work? Well, let's say we have here in the bottom left corner of the panel, here we have in the unperturbed trajectory, in the background trajectory, we have the field and its momentum at ni. So we pick ni, this initial reference time for delta M formalism, we take it here. We perturb the field along the blue line, which has this slope here, so it is in agreement with this consistency condition. The field is perturbed along this line, and then we let it evolve along the corresponding trajectory. And this perturbation here and the subsequent rolling around here will induce a difference in the total number of efforts until the end of inflation, which is precisely the delta M we are looking for. And the nonlinear relation between how much we perturb the field here and how much it takes to get back to its trajectory is the nonlinear relation between inflaton and curvature perturbations that we are looking for. There are two phase spaces here because I will consider two models as we did in this paper. One of them is a model in which the attractor in phase space, so the convergence of the gray trajectories, is a constant roll attractor, meaning that it is, as I said before, a straight line in phase space, and it is superimposed on the blue line, which is the constant roll line, giving you the direction of the perturbations. In this other case, there is again this blue line, so the constant roll line giving the direction of the perturbations, but the attractor in phase space is not a constant roll attractor. It does not have a constant slope. For the stochastic formalism of inflation, the picture is a bit different of what I have just described. In the stochastic case, the inflaton moves along the unperturbed trajectory and it receives at each time step kicks that are parallel to this blue line, again in agreement with this consistency condition. And the accumulated effect of these peaks results in a delay until the end of inflation, which is the delta N again we are looking for. Okay, so before moving into the comparison between stochastic and delta M formalisms, let me review a couple of standard approximations that have been used in the literature. The first one of them is what we have called in our paper the unperturbed trajectory approximation. This has been used extensively because it's very economical from a computational point of view, and it essentially consists on perturbing the inflaton not along the blue line, which would be what is in consistency with this condition here, but along the background or unperturbed trajectory. So for instance, instead of having a large perturbation that brings the field here, it would bring it down here, and then the field would evolve from here onwards. Just by looking at the phase space, we see that this approximation will be a good approximation as long as the unperturbed trajectory and the blue line coincide. So around here for this model and here for this model, but it will eventually fail. And this is precisely what we see when we plot the PDF, so the black line is the full calculation, the one in which the field, is consistently perturbed along the blue line. This produces the usual exponential tails that people have reported in the presence of ultra-slow roll phases. And the unperturbed trajectory approximation coincides well for both models for small perturbations, but eventually it fails, and the failure corresponds to this departure here between the blue line and the dashed line. And as we argued in our recent paper, this failure is always takes place in the characteristic shape of a bump, so a slight increase followed by a super exponential cutoff. The next approximation I want to study, which is also a very useful approximation because it allows for analytical calculations, is what we call the eternal constant roll approximation. And this essentially assumes that the field is both perturbed and then evolved along a line of pure constant roll, so a purely straight line in phase space. Of course, this will be a very good approximation for this kind of models, because if the field is sitting here at an eye, it is indeed perturbed and then evolved along this constant roll line, which is the superimposition of the perturbation blue line and the attractor, the constant roll attractor in phase space, but it will not be a good approximation for this kind of models in which the field, yes, it's perturbed along a constant roll trajectory, but then evolves along trajectories that are not of constant roll. They have a change in slope. Again, if we go to the PDFs, we see that it is a good approximation for this case, but it is a bad approximation here. It breaks at this point, which corresponds to this departing point here. And now we move to the main point of my talk, which is the comparison between classical and stochastic delta informalisms. So it had already been argued in this paper that for this kind of models, in which we have pure constant roll phase space, the two approaches, classical and stochastic, are equivalent. And the reason why they're equivalent is because in the constant roll case, the equations of motion for the inflaton are linear. Therefore, the superimposition of many small kicks, Gaussian kicks, which is what the stochastic formalism of inflation does, is equivalent to having one large kick, which is essentially what the classical delta informalism is doing. In this other case, however, there is no guarantee in principle that this equivalence is going to hold still. What we found in our recent paper is that actually it does, provided that the power spectrum has a narrow peak, which is not a strong assumption for an ultra-slow roll model, which predicts narrow peaks in the power spectrum anyway. So let's say that in this case we have an exact equivalence, and in this case we found out that there is an effective equivalence. Despite this equivalence, there are qualitative differences between both models, which I want to highlight at this point. The most important of them is that while in this model we have the usual configuration of a Gaussian PDF that turns into an exponential tail, in this case the exponential tail doesn't have a constant slope. It's like a broken exponential. It has one slope here and one slope here, and these two different slopes are related to the fact that the attractor itself has two different slopes, if you want, one here and one here. This in turn induces another difference between this model and this model, which is that while for this model there is, to a large extent, an independence of the PDF of zeta or delta n on the choice of an I, as again it was already argued in this paper, and we came back to this in our own paper. In this other case, there is a strong dependence on the shape of the tail of the PDF, the exponential tail of the PDF, on the choice of the initial time in the classical delta informalism. And again, we can understand this by going back to the phase space. What is going on here is that if I take an I to be here, I need a very large perturbation to bring me back to the region of phase space in which I will be able to probe this part here of the attractor that has a different slope. However, if I take an I to be here, I need a much smaller perturbation to bring me back to this region in which I see this part of the attractor with a different slope. Therefore, the earlier I take an I, the earlier, so for smaller perturbations, I will see this flattening of the tail of the potential that is characteristic to this second model we studied. Okay, and before concluding, I want to discuss an important remark regarding this effective coincidence or this effective equivalence between the classical and stochastic delta and formalisms that we found for this kind of models in which a priori it is not guaranteed, which is this consistency relation relating two important parameters, the coarse graining parameter from stochastic delta n and the Ni parameter from classical delta n. So sigma, the coarse graining parameter in stochastic delta n, as I mentioned before, tells us about the delay between a mode exiting the horizon and the same mode kicking the background. In the classical delta n formalism, Ni tells us about the time in which we perturb the inflaton to see what is the response in terms of number of EFOLs until the end of inflation. What this consistency condition tells us is that Ni should be taken such that it is the moment in which the mode corresponding to the peak of the power spectrum gets coarse-grained and it kicks the horizon. Let us see this with an example. So this is the orange crosses here are the PDF for zeta or delta n computed in the stochastic delta n formalism with a sigma of 0.01. In order to reproduce this result with classical delta n, which is what is done in the black line, I should take the Ni for the classical calculation to be minus log of sigma, in this case minus log of 0.01, EFOLs after n peak, which is the horizon crossing of the peak of the power spectrum. That is 4.6 EFOLs. Actually, the best fit is not 4.6, it's 4.9. This small offset is because the peak of the power spectrum is not an exact Dirac delta, but it has some width we have to account for. But in any case, 4.6, 4.9 ballpark. To compare a counterexample, if I compute this PDF in a stochastic inflation but with sigma 0.1, the agreement is not there anymore with the classical delta formalism, because in this case Ni should be minus log of 0.1, that is 2.3 EFOLs after the coarse graining of the horizon crossing of the peak of the power spectrum. And with this I arrive to my conclusions. We have seen that provided that this consistency condition holds, classical and delta n and stochastic delta n formalisms actually predict the same non-Gaussianity for the PDF of curvature perturbations, whether we are in a model with a constant roll attractor or not. And this implies that the origin for these not Gaussian but exponential tails is not the way we treat inflaton perturbations, stochastic or classical, but the nonlinear relation between inflaton and curvature perturbations. This is good news because classical delta n is numerically much cheaper than stochastic delta n, and also it allows for a number of approximations whose regime of validity we have studied. And with this, I will conclude my presentation. Thank you very much for your attention, and looking forward to seeing you in the discussion session.